Yeah.
Why did I give you guys choices?
I don't know.
I shouldn't do that. Should be no choice. All right, so minus 1 is e to the pi I. And so there you go. We get minus a e to the pi I. Pi ia is the way we could write the residue there. All right. Now, so the Cauchy residue theorem in this context, right? We've got the integral over the outer circle, the integral along the lower L minus, and the integral along the upper L plus, and then the integral around the little circle gamma sub epsilon. We know that that all works out to minus 2 pi I a e to the I pi a because we just worked out the residue right above, all right? For the outer circle, notice that we can bound the integrand z to the a over 1 plus z squared by r to the a divided by r minus 1 quantity squared, right? Assuming that r is, I guess it even doesn't matter if r is greater than 1. That's just true. Oh, wait a minute. No, that does matter. So here I'm using, what am I using? How did this change to r minus 1? Which I'm using this thing we talked about last class, right? Modulus of z plus 1 is greater than or equal to the absolute value of the modulus of z minus 1. And if the modulus of z is equal to r, this is equal to the absolute value of r minus 1. All right? So we are, I mean, I'm assuming, I should probably assume that like the r is greater than 1 for this calculation. Otherwise, I could have division by 0 there, which would be a little bit off-putting, you know? Right? Uh-huh. Oh, we'll find out.
You actually wrote that R almost wrong. I might have wrote it wrong. Where you said the absolute value of z plus 1 is less than. I must have wrote that wrong.
Well, maybe no. If you have the I mean, it's also true that the absolute value, the modulus of z plus 1, right, less than or equal to modulus of z plus 1, that's just the usual triangle inequality. This is a corollary to the triangle inequality that's useful for us in the context of denominators because we want to make a fraction larger, so we need to make the denominator smaller, which is what's happening here, all right? And also a is a real quantity, so like, you know, that's also something that's helping this calculation. But, so we have that bound on this integrand for that curve. On the other hand, for the epsilon circle, we have this, this bound here, all right? Okay, so then what? Well, by the ML estimate, right, the ML theorem, the integral over gamma r is less than or equal to m, which was r to the a over r minus 1 squared times 2 pi r. But that is r to the a minus 1 divided by 1 minus. So this, as r goes to infinity, we have both of these. That goes to 1, right? And since the what's the word? Since the absolute value of a is less than 1, right, and not equal to 0, that means that this power, as r goes to infinity, goes to 0. Because it's either, well, anyway, if you just sort through it, if a was negative, then it's, you know, reciprocal. Anyway, for any a less than 1, I believe this is reciprocal, right? So I don't see that a equals to 0 is problematic for this one. Yeah. Now down here, oh, so that my explanation's right here, right? A minus 1 is less than 0, so that's a reciprocal power of r, which goes to 0 as r goes to infinity. Now on the other hand, a plus 1 is greater than 0. And that gives us that. This right here I can rewrite as that. and that goes to 0 as epsilon goes to 0. Why is that? Does that make sense? Because this is a positive power, right? And of course the denominator goes to 1, and this goes to 0 as epsilon goes to 0. The point is that both this integral and that integral are squashed as we allow the contour to, squeeze in on the origin and go out to infinity, right? So we're just left with the integrals along L plus and L minus, all right? Now, there we just need to be careful. L plus is pretty simple. L plus is the one that's got the argument of 0. So for the argument of 0, when we work out z to the a, we just get x to the a. Because, you've got x to the a equals to exponential of a natural log of the absolute value of x. There's no, the thing is 0, right? So this just literally works out to, I should write z to the a over here to make it more not seem like I'm not doing anything. So this is for like L plus, right? For the other one, you've got this 2 pi I up here for the L minus, right? And that 2 pi I matters. That 2 pi I matters because it hits the A, right? It produces what's called a phase factor, right? So, and I reverse the orientation so that I can simply parameterize the integral by z equals to x. Because it's the integral is going to the left, so I actually pull a minus out to make it go to the right. I think I'm supposed to have a minus down here, technically speaking. Anyway, so no, this is fine. This is fine. This is equal to that. Let me not get distracted by this. So we have x to the a, e to the 2 pi I, again, because the complex power function puts the phase factor in there. When we multiply the a times the 2 pi I, we get that, right? So we don't get the same integral above and below the positive x-axis. We get slightly different integrals. So when you put that all together, you've got the integral from the L plus, the integral from the L minus, right? And the minus, again, is coming from the fact that the L minus was going from right to left rather left to right. That's what the minus is for. It's to account for the fact that the direction of the L plus and L minus were opposite. So when you actually parameterize the integral in terms of z equals to x, you got to put the minus in. And that's the phase factor that comes because that is technically below the positive x-axis where the angle is 2 pi. So you get this minus that. And so we're interested in this integral, so we solve for it. So you just factor out 1 minus e to the 2 pi I, and then divide. And there you go, this integral is equal to that, which, after you do some, test 1 kind of calculations, you should get pi a over sine pi a. So there you go, this integral is equal to that. Was that Gamelin? Oh yeah, Gaiman. Gamelin remarks that the function g of w equals x to the w dx over 1 plus x squared is analytic on the strip minus 1 less than real part of w less than 1, as is the function pi w over sine pi w. Thus, by the identity principle, we find that the principle. Yeah, we find that the integral identity holds for minus 1 less than that, Let's see here. Yeah, that integral. So this is called an integral with a branch point. Here's another one of those. Maybe we'll look at that next time. But so these are like strategies that, we just looked at an example which put the branch cut there, right? These are sometimes called keyhole contours because it's like a keyhole, And of course you could, you could put the branch somewhere else. You could do something like this or like that. And so anyway, I think this is pretty different than the previous two things we did, right? But anyway, we shall do more. Just a little bit at a time. Thanks, guys.